आज जैनिल आदित्य ने भी, अरे इसने भी दिया है, क्या नाम इसका, दानिश।
हम्म। ए में डाउट है किसी को? क्या
नहीं।
था? ठीक है, डिस्कस कर लेते हैं। ओके। Chef and his family is trying to reach the airport, including Chef. They are a total of n members. A single cab ride costs this much rupees to transport X people from Chef's home to the airport. Further, a cab can fit at most 4 people. So we have to minimize the cost required for the chef's family to reach the airport. Okay. So a single cab ride costs this much. Okay. Max of 200, comma x times 100, where x is the number of people in that cab. So let's see the test cases. So if there was only one person, how much cost would he require? He would require a max of 200, comma 100, because x is 1, which is 200. Therefore, the output here is 200. If there were two people, they would require max of 200, comma 200, because x is 2 here, and this would be 200 as well. If there were three people, it would require max of 200, comma 3 times 100, which is 300, which is 300. Similarly, for 4, this would be 400. Now, for 5, we can make the people go in two cars. One car will hold two people, one car will hold three people. And it would take them 200 plus 300 rupees to get to the airport, which would be 500. So the thing to notice here is there is only one case, which is when there is only one person, when the cost will be 200. Uh, so only one person is taking will take like 200 rupees to get to the airport, and there will be only one case for this. Otherwise, all people will take only 100 rupees. So it would take 100 rupees per person to get to the airport, and the answer would be the number of people times 100, x times 100. So that's it. If n equals 1, we can just output 200, or else it will always be n times 100. That's it. Okay. Any doubts in A? Hello.
हाँ हाँ, you're audible. कौन सा क्वेश्चन?
No doubts in A, right? Can we go on?
Yeah.
Cool. Okay. So the second question says that we are given a weighted undirected graph on n vertices and we have n times n minus 1 by 2 edges, which means that each node is connected to every other node. Uh, each edge is assigned a certain weight, and however, the weight has been scrambled, and we have recovered the multiset of weights, but we don't know which edge had which weight initially. So we are just given this multiset of weights. Among all possible assignment of weights, what is the maximum possible value of the minimum spanning tree? Okay, and we are given the definition of minimum spanning tree. Minimum spanning tree is a subset of n minus 1 edges with the minimum sum of weights in the subset. However, we are supposed to maximize the value of the minimum spanning tree in this case. So, okay, let's take an example. Let's say we are given two nodes. Nodes are 1 and 2, and we are given an array of size, a multiset of size n into n minus 1 by 2, which is the number of edges. Okay, so we are given for the 2 case, we are only given a multiset of size 1 and the weight is 42. So we don't have any other option to make this a minimum spanning tree except to just connect these two and assign them the weight 42 because we only have one weight here. Uh, let's take this case 3, 1, 2, and 3. Okay, so we are given edges weight as 1, 2, and 3. So here we can connect 1 and 2 as 1, and we can connect 1 and 3 or 2 and 3, and we can assign it as 2, and the value will be 3. Let's take a better example. Let's say we are given 5 nodes, 1, 2, 3, 4, and 5. And let's say we are given the multiset as 1, 2, dot 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 till 5 into 4 by 2, which is 10. Okay, so this is the multiset we are given, and we are supposed to maximize the minimum spanning tree formed using these 5 nodes. Okay, so any minimum spanning tree algorithm, how does it exactly work? We first take the minimum cost. Okay, so the minimum edge cost here is 1, right? So we will just assign 1 anywhere, let's say here for now. Then we can assign the cost 2 here. Then we can assign the cost 3 here. However, since we are supposed to maximize the cost of the minimum spanning tree, uh, we can assign 3 here. Now, since this forms a cycle, this won't be taken into account. And we can assign, can you mute please, Viga? Cool. Okay. So this 3 node becomes redundant as we just assign it here. And 1, 2, and 3 were already connected, even if it wasn't for this node with weight, or even if it wasn't for this edge with weight 3, right? So like this, we can just make this 3 node redundant and we can just assign it here. Next, we can assign 4 here Now we can assign 5 here, and now this node is also redundant. This edge is also redundant, these two edges. And we can assign 6 here. Then we can assign 7 here. And now we can assign 8 here, 9 here. Now these two nodes are also not taken into account since 1, 2, 3, 4, 5 were already connected without using 8 and 9 weighted nodes. Then we can just assign the last weight 10 here. And now our minimum spanning tree is maximized. And it has value 1 plus 2 plus 4 plus 7 plus 10, which is 22. And this will be the maximum cost possible for this to construct this minimum spanning tree. Okay, so that's it. That was the algorithm. So how can we implement this algorithm? We can notice that for the first weight, we can always assign it to a certain two nodes. Then the second weight, also we don't have many options because we cannot assign it in the same side. So we can assign the second weight. So I'll just write this as first, second. Now the third weight, we can make it redundant and we can just assign it right here, right? Because we can form a cycle using the third weight. Uh, and we can use the fourth weight here. Then for 4, we can make 2 more weights redundant by connecting them to this node and this node. So 5 and 6 are gone, and we can assign 7th here. Then we can assign, then 5 can also make 3 more nodes redundant, and we can assign the 10th weight here. Okay, so we can notice a pattern here. This is plus 1, plus 2, plus 3, plus 4, and so on. Okay, so yeah, that's the algorithm. We can just sort these weights and we can assign the first, second, fourth, seventh until we reach, how many times do we do this? 1, 2, 3, 4, 5. And how many nodes do we have? We also have 5 nodes. So we can do this n times. Yeah. So I just took the input here of all the weights and I sorted them in ascending order. Now, the first answer will always be the first element and then the second, then the fourth. So I initialize the increment as 1 and then I do this is where the total answer is stored, and I keep adding v of ptr. Ptr is the current pointer at which we are at, and I keep incrementing pointer by inc, the increase variable, and then I also do increase plus plus because initially we are increasing by 1, then we are increasing by 2, 3, and so on. And I do this n minus 1 number of times. That's it. Any doubts in this question?
In this question, we do not need to sort the vector also because it is the elements are coming in multi-set.
Right, yeah. Yeah, they are coming in multi-set, so it is already sorted. Right,
Okay.
cool. Okay. Third question from div 2. You are given a zero indexed binary string s of length n plus 1 and your task is to construct an array of length n such that these conditions hold. What do these conditions basically say? That whenever we find a subset whose max is equal to a certain value in this array, then the string value of that array of that element should be 1, or else it should be 0. So we are supposed to find an array such that this input string satisfies. Okay. Let's just take a test case for this. Okay, so 1, 1, 0, and 0. So for this, the output that they have provided is 0, 2, and 0. Okay, so why does this satisfy? This is a 0 based string. So this is indexed as 0, 1, 2, 3. Okay. Now, can we pick a subset from this array such that the max of that subset is 0? Yeah, so we can just pick this subset, and it is possible to make any subset of this, a certain subset of this array, sorry, a sub array of this array to have the max 0. So we can just pick 2 as the sub array, and the max of this is 0. Therefore, the value here is 1 because it is possible to make the max 0. Now, can we make the max 1? So we can just pick this or this. For this subarray, the max will be equal to 1. Now, can we make the max 2 in this array by picking any subarray? So for max 2, we will need both the elements 0 and 1 to be present in subarray, and it is not possible in this array. So therefore, the value here is 0, and similarly, we can't make 3. So the value here is 0. Alright, let's take a better test case. Let's take 1, 1, 0, 0, and 1, 1. Okay, this is my string. The index is 0, 1, 2, 3, 4, 5. Okay, now let's try constructing a 5-sized array for which this string satisfies. So the one thing to notice is that if we include any non-zero element in the array, in our array, the max 0 will always be possible because we can just pick that element. Right. It is also mentioned that s of 0 equals s of 1 equals 1 because we can always make these two 1. Right. Okay, so now we can focus on making the max of any subarray to be 4. So let's just consider this 0, 1, 2, 3, and we also need the max of 5 to be 1. So max 5 should be possible. So let's also take 4 here. However, this will make the max 2 also possible, as we can just pick this subarray. It will also make the max 3 possible. We can also pick this subarray. So we are supposed to avoid this. So how can we avoid this? What we need to figure out is how do we not let the 0, 1 elements come one after the other. So one thing we can do is we can just put 2 here and maybe put 1 here. So the array will become 0, 2, 1. And now it is not possible to make the max to be 2 using any subarray because this 2 element will always come in between 0 and 1, and the max will at least be 3 here, right? So that is the one thing to notice. So okay, so the rest of the array will look like this, and we have satisfied this while not affecting this and this because we can still pick this entire subarray, the max becomes 4, and we can pick this subarray and the max becomes 5. Okay, so however, we also need to make this 0. Even here we can pick this subarray and the max will be 3. So we need to avoid that. So again, we can also put 3 here. We can swap these two values basically to make it look like this. Now it is not possible to make the max of any subarray to be 3 because the elements 2 and 1 are separated by 3. So the max of this will be at least 4, right? And now this array satisfies every condition for this string. We can make the max, we can always make the max 0 and 1. We cannot make the max 2 now because 0 and 1 are separated by certain elements and which includes 2. So the max, even if we pick all this, the max will be greater than 2, right? And we have also separated this because the max of, we cannot make the max 3 again because 2 and 1 are separated by 3, right? So this array satisfies. Now, however, what if this element right here is 0? What if this happens? Okay, so right now we are taking all the elements from 0 to n minus 1. So the max of 5 will always be possible here. But what if we need to avoid any subarray having the max 5? So we can just replace this element by 5. Now 4 is not available, so the max can never be 5 if you pick any subarray here. Right. So that's all I'm doing in my code. 0, 1, 1, 0, 0, 1, 0. So I'm initially assigning everything as I'm initializing a vector with values 0, 1, 2, 3, 4, and 5. And whenever we don't need the max to be this element, like whenever the string is 0, which means that we don't need the max to be 2, then I'm just swapping this and its previous element. So I'm swapping this. This becomes 0, 2, 1, 3, 4, 5. Now when I encounter this, I'm again swapping this 0, 2, 3, 1, 4, and 5. And yeah, let's just take this as 0. This is the string. So since this is 0, I'm swapping these two values 0, 2, 3, 1, 5, and 4. And now I'm just outputting this vector except the last element. That's it. Okay. Yeah, this is my code for the same. Any doubts? Hello.
No.
Okay.